Okay, video number 2 is going to be the derivation of our spring potential and gravitational potential energy formulas. All right, I'm going to talk a little bit about the kinetic energy formulas as well. So let me start here. It turns out that the area under a force versus distance graph, F delta x, the area under that curve is work done by that force over that distance. All right. Now, work and change in energy go hand in hand. It turns out work is change in energy. Oops. Work is change in energy. That could be potential energy, kinetic energy, whatever it might be. You have to be kind of flexible here. Whether or not those are positive or negative kind of is subtle as well, but don't worry about that for now. So, sketch the spring force versus distance graph from the lab below. Okay, there it is. Produced. I gotta edit this worksheet. All right, the area under this curve tells us the amount of potential energy stored. We'll call it stored in the spring. So we'll call it PE spring, potential energy. It's going to be 1/2 base times height. Or it's the work done on the spring to compress it. You have to think of it either way. So if you do work on the spring to compress it, you're storing potential energy. If the spring does work on an object and releasing that potential energy, then that's gaining kinetic. So potential energy goes up, kinetic's got to go down. If kinetic energy goes up, potential has to go down. They're related to each other in that respect. So 1/2 base times height for this graph. All right. So I'm going to say I stretch it to some spring, some position, right? Some sort of position X, some sort of spring force up there to hold it in that position. So PE spring, it's 1/2 base times height. So it's 1/2 of the base here, which is however far you stretched it, times the height, which is the force required to hold it in place. All right, but then we take this a step further and we say, okay, spring force equals the constant, spring constant, times however far the spring is stretched or compressed. All right, so we put that in there. We get 1/2 of x times kx. We get 1/2 kx squared. So this is the formula we use for spring potential energy. So potential energy stored in a spring is equal to 1/2 of the spring constant times however much the spring is compressed or expanded. All right, so I got this from the area under the curve calculation here. We could also use calculus to do this, but I don't want to do that. You can do something called an integral of the force function and get the energy function. But in algebra-based physics, we just use area under the curve to figure stuff like this out. So at the end of the day, this mumbo-jumbo, really this is what you need to know. This formula, which is on your equation sheet. The amount of energy stored in a spring when it's compressed is equal to 1/2 of the spring constant of the spring multiplied by the distance it is compressed or expanded squared. Don't forget that squared part. It's important. All right. Now we can do the same thing of force of gravity versus height graph for lifting an object off the ground. So if you lift an object off the ground and you plot the force of gravity resisting you as you lift it up, as the height increases, it turns out that that is a flat line in a classroom close to the surface of the earth. So the area under this curve will tell us the amount of gravitational potential energy stored in an object when you lift it off the ground. So PEG equals, I don't need to do 1/2 because it's a rectangle, it's just base times height. So the base here is however high you've lifted it off the ground. The height of the rectangle here is whatever the force of gravity is acting on the object. Well, the force of gravity acting on the object is mg, and we usually rearrange this to be mgh. So when you have something lifted off the ground, for instance, some block of mass m, its potential energy is mg times h, where g is about 10 newtons per kilogram, or 10 meters per second squared. All right, so that's another formula for the reference table. Now, here we go. The work energy theorem tells us that the change in kinetic energy of an object from applied forces is equal to the net work done on the object. So I've basically been saying that, but this is it in an equation. The change in kinetic energy of an object is equal to the net work done on it. So if you look at all the forces acting and boil it down to the net force, that net force acting on the object times however far it's moving for, its displacement, gives you the change in kinetic energy. Now, kinetic energy is the energy of motion of an object, all right? 1/2 mv squared. Now, the derivation of this formula, I can show you here. So, change in kinetic energy equals F net times displacement. F net is MA, right? MA times the displacement, delta x. Well, there's a couple ways to do this, right? You could use the v squared formula, right? If you know the final velocity, initial velocity. So let's say, let's look at the v squared equation, right? Let's write that down here. V final squared equals v initial squared plus 2a delta x. So, a delta x. I see that here. I see it here. Let's see what we can do. So I'm going to bring v final squared minus v initial squared equals 2a delta x. Divide by 2. I get a delta x equal to v final squared minus v initial squared over 2. So now I take that, plug it back in here for a delta x, right? I get change in kinetic energy equals m times v final squared minus v initial squared divided by 2. I just expand this out a little bit, bring the 1/2 in front, the m with it, v final squared minus 1/2 mv initial squared. So if change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared, then just Ke by itself must just be 1/2 mv squared. So, you can do this. Again, this is probably better solved with integration, but that's just a basic of where it comes from. This we'll look at a little later on. At the end of the day, those 3 equations I just derived are important. Those are what are going to be on an equation sheet. So I'm going to recap them on the back of this page here for you. So we have, at the end of the day, we have work equals force times displacement. We've got work net equals F net times displacement, which equals change in kinetic energy. We have the potential energy stored in a spring, or stored in an object from a spring, I probably should say, is 1/2 kx squared. I have potential energy stored in an object when lifted off the ground is mgh. And we have the kinetic energy of something while it is moving is 1/2 mv squared. All right, that's pretty much it for now. As we get moving on this worksheet, we will do a little more work. I think in class we left off here, right about here, and we're gonna get down in here. So we're just gonna practice using the kinetic energy formula first here, and then we're gonna do some problems back here, trying to determine final speeds and such.